Welcome to today's problem walkthrough. We're exploring LeetCode problem number 425, word squares. In this problem, we'll tackle the challenge of constructing a grid of words where each row and column must form valid words from a given list. Let's dive into the details and solve this step by step. A word square is a fascinating arrangement of words in an NXN grid, where every row and every column spells out a word from a given list. For example, in a 4x4 grid, we might have the words ball, area, lead, and lady. Here, not only do these words form valid rows, but reading down each column also gives valid words from the same list. The challenge here is to construct all possible word squares using a given list of unique strings. Each square must include exactly n words, where n corresponds to the length of the words in the input list. The order in which the results are returned doesn't matter, as long as we identify all valid combinations. To solve this problem, the input will be a list of strings, where each string consists only of lowercase English letters. In terms of output, we need to return a list of lists. Each sublist in this output represents a valid word square, with exactly n rows, each containing n characters. Let's look at an example to understand this better. Suppose the input list of words is area, lead, wall, lady, and ball. The output would be a list containing two word squares. The first square uses the words ball, area, lead, and lady, while the second square uses wall, area, lead, and lady. Both grids meet the criteria since their rows and columns form valid words. Now, let's break down why these word squares are valid. In the first word square, the rows are ball, area, lead, and lady. If you read down the columns, you also get ball, area, lead, and lady, which are all valid words from the input list. Similarly, in the second word square, the rows are wall, area, lead, and lady. Again, reading down the columns gives wall, area, lead, and lady, which are valid words. This demonstrates how the rows and columns must align perfectly to satisfy the word square conditions. Let's consider another example to further illustrate this concept. In the second example, the input list of words is abat, baba, atin, and atal. Here, the output contains two valid word squares. The first square has rows baba, abat, baba, and atal. Reading down the columns, you get baba, abat, baba, and atal, which are all valid words. The second square has rows baba, abat, atin, and atal. Similarly, reading down the columns gives baba, abat, atin, and atal, ensuring that both rows and columns are valid. This reinforces the idea that each row and column must independently form a valid sequence of words. Now, let's discuss some important constraints and edge cases to keep in mind. All words in the input list will have the same length, which is crucial for forming NXN grids. The words consist of only lowercase English letters and are guaranteed to be unique. Regarding constraints, the number of words in the list can range from 1 to 1,000, and the length of each word is between 1 and 5 characters. For edge cases, if the list contains just one word, that word forms the only valid word square. If no valid square can be constructed, the output should be an empty list. The solution must also efficiently handle small grids, such as n equals 1, and larger grids, up to n equals 5, ensuring scalability within these limits. To solve the word squares problem, we need to construct an n by n grid where every row and column represents a valid word from the input list. Let's start by examining two possible approaches. First, the brute force approach. The idea here is straightforward: generate all possible combinations of n words from the list and check if they form a valid word square. To validate, we ensure that for every ith row and ith column, the characters align correctly. However, this method is computationally expensive. The time complexity grows exponentially with the size of the word list in grid, making it impractical for larger inputs. The second approach is backtracking with prefix pruning. Here, instead of testing all combinations, we construct the word square row by row. To optimize this process, we only consider words that match the prefixes formed by the current rows. By using a prefix-based filtering system, we eliminate invalid candidates early, significantly reducing the search space. A tree or hash map can be used to store words grouped by their prefixes, enabling efficient lookups during backtracking. This approach has a much better time complexity and avoids unnecessary computations. The backtracking with prefix pruning approach offers significant performance improvements, but it requires additional space to store the prefix dictionary. To further optimize, we can use a tree-based structure. A tree organizes words hierarchically by their prefixes, making prefix lookups even faster. During backtracking, instead of filtering candidates from a flat list, we traverse the tree to find valid candidates, which reduces the overhead of searching. While the time complexity remains similar to prefix pruning, the use of a tree can make the process faster in practice, especially for large datasets. However, this comes at the cost of increased pre-processing time and memory usage. After evaluating these strategies, the backtracking with prefix pruning method was chosen as the primary solution. It strikes a balance between efficiency and simplicity. The tree-based optimization, while faster for extremely large inputs, adds complexity and memory overhead that may not be necessary for most problem constraints. Meanwhile, the brute force approach is not practical for larger inputs due to its exponential complexity. There are a few key observations that make the backtracking with prefix pruning approach particularly effective. First, valid word squares must satisfy both row and column constraints. By leveraging prefixes, we can enforce these dual constraints efficiently. Prefix pruning significantly reduces the search space by eliminating invalid candidates early in the process. Additionally, using a tree or prefix grouping ensures that only relevant candidates are considered at each step, avoiding unnecessary computations. Comparing the different approaches, brute force is straightforward but not scalable for larger inputs. Backtracking with prefix pruning is a more efficient solution, especially when paired with prefix optimization techniques. While using a tree offers faster prefix lookups, it comes with higher pre-processing and memory costs. Ultimately, backtracking with prefix pruning provides a good balance between simplicity and performance, making it the optimal choice for solving the word squares problem under typical constraints. The word squares problem challenges us to construct valid NXN grids where both rows and columns form words from the given list. This dual constraint, ensuring that rows and columns align, is what makes the problem intricate. To tackle this efficiently, we use a combination of backtracking and a tree data structure. Backtracking allows us to explore all possible configurations, while the tree helps us quickly identify words that match a given prefix. The first step in this process involves building the tree. We initialize the tree and insert each word from the input list. During insertion, we store a list of words associated with each node in the tree, representing all words that share the prefix up to that point. This design enables fast lookups during the backtracking phase and helps prune invalid paths early on. Once the tree is ready, we begin the backtracking process to construct the word squares. Starting with an empty list named square, each word in the input list is treated as the first row of the grid. The word is added to square, and we recursively attempt to build the remaining rows. For subsequent rows, the prefix for the next word is determined by the characters in the current column of the grid. Using this prefix, we query the tree to retrieve all matching words. Each matching word is added to the grid, and we continue the recursion until the grid reaches the desired NXN size. At this point, the completed grid is added to the result. If a configuration fails to form a valid grid, we backtrack by removing the last added word and exploring other options. This systematic approach ensures that we explore all valid combinations while leveraging the tree for efficient prefix-based filtering. The efficiency of this algorithm lies in three key insights. First, the tree enables prefix pruning, allowing us to eliminate invalid paths early in the backtracking process. By storing words in the tree and maintaining prefix-based lists, we avoid unnecessary searches and significantly reduce the search space. Second, the column constraints ensure that the word square property is preserved, as each prefix is dynamically constructed from the characters in the current column. Finally, the backtracking mechanism balances thorough exploration with efficiency by pruning paths that cannot lead to valid grids. In terms of data structures, the tree is central to the optimization, enabling fast prefix lookups, while the square list temporarily holds the grid being constructed, making it easy to modify and backtrack as needed. To implement the algorithm, we perform three key operations. First, inserting words into the tree ensures that prefix lookups are efficient, with each insertion taking k time, where k is the word length. Second, the prefix search operation retrieves all words matching a given prefix, also in OK time. Third, row construction dynamically builds rows based on column constraints, ensuring that the word square property is maintained. Analyzing the complexity, tree construction takes M*k, where M is the number of words and K is the average word length. The backtracking process depends on the number of valid word squares and the branching factor, which can approach n to the power of n in the worst case. However, tree pruning significantly reduces this. For space complexity, the tree requires M*k, and the recursion stack depth is n, corresponding to the grid size. When implementing this algorithm, it's essential to handle edge cases carefully. If the input word list is empty, we simply return an empty result. Additionally, all words must be of the same length n, as this is required to form a valid nxn grid. If no valid word squares can be formed, the algorithm should account for this and return an empty result as well. To better understand the process, consider an example where the input words are area, lead, wall, lady, and ball. First, we build a tree with these words, ensuring each node tracks words sharing common prefixes. During backtracking, we might start with wall as the first row, then determine the prefix for the second row, which is based on the second column. From the tree, we retrieve area as a matching word and continue recursively. This process repeats until a valid grid like wall, area, lead, lady is formed. All valid grids are then returned as the result. Here, we start by defining a solution class with a method called wordSquares that will handle the problem. The first step is to create a helper function called build_prefix_map. This function constructs a data structure, specifically a dictionary, to store prefixes of words. Using Python's defaultIct, we map each prefix to a list of words that share that prefix. For every word in the input list, we iterate through its characters and progressively build prefixes by slicing the word up to each character. These prefixes are then added to the dictionary along with the word they come from. The result is a comprehensive lookup table that allows us to quickly find all words matching a given prefix. Next, we define a backtracking function that will help us construct the word squares. This function takes two arguments, step, which tracks the current depth in the word square, and square, which represents the current partial word square being built. If the step equals n, meaning that the square is complete, we append a copy of the square to the results list and return. Otherwise, we calculate the prefix for the next word by iterating through the current square and extracting the letters at the step index. Using this prefix, we fetch all candidate words from the prefix map. For each candidate, we add it to the square, proceed to the next step with a recursive call, and then backtrack by removing the last addition once we return. Finally, we initialize n as the length of the words, which is consistent for all words, and call build_prefix_map to prepare the prefix lookup table. With the prefix map ready, we now define an empty list called results to store our final word squares. The main logic begins by iterating through each word in the input list. For each word, we treat it as the starting row of a potential word square. We call the backtracking function with the first step set to 1 and the initial square containing just the current word. The backtracking function will then recursively build all valid word squares starting with this word. Once all possibilities are explored, the results list will contain all the word squares that can be formed from the given words. Finally, we return the results list as the output of the method. This iterative and recursive approach ensures that we systematically explore all combinations while leveraging the prefix map to efficiently narrow down the choices at each step. Here, we begin by defining our solution class and the wordSquares method, which takes an array of words as input. Since all words in the problem are guaranteed to have the same length, we can determine the square size using the length of the first word. Next, we create a prefix map to store all possible prefixes and their corresponding words, which will help us efficiently find candidates during the backtracking process. After building the prefix map, we initialize a list called results to store the final word squares. For each word in the input array, we treat it as the starting word of a potential square. We create a temporary list called square to represent the current square under construction, add the word to it, and call the backtrack method to fill in the remaining rows. The word squares method ultimately returns the list of all valid word squares. The build prefix map method creates the prefix map by iterating through each word and generating all of its prefixes. For each prefix, we add the word to a list associated with that prefix in the map, ensuring efficient lookups later. Moving on to the backtrack method, this is where the recursive logic for constructing word squares is implemented. The method first checks the base case. If the current step equals the size of the square, it means the square is complete, so we add a copy of it to the results list. Otherwise, we need to construct the prefix for the next word in the square. To do this, we iterate over the current square and collect the character at the current step from each word, forming the prefix. Using this prefix, we retrieve the list of candidate words from the prefix map. For each candidate, we add it to the square, recursively call backtrack to continue building the square, and backtrack by removing the last added word to explore other possibilities. Finally, we close the class definition. By combining the prefix map and the backtracking approach, this implementation efficiently constructs all valid word squares while systematically exploring all possibilities. The recursive design ensures that all combinations are considered, and the use of the prefix map optimizes the process of finding candidate words, making the solution both elegant and performant. To solve the problem of building word squares, we begin by constructing a prefix map. This map is a dictionary where each key is a prefix of a word, and the corresponding value is a list of all words that start with that prefix. For example, with the word area, we generate prefixes like an empty string, ar, and r, and map them to the word area. Similarly, for lead, we add prefixes like l, lu, and lia. By iterating over all the words in the input list, we systematically add their prefixes to the map. The result is a comprehensive prefix map that allows us to quickly retrieve all words matching any given prefix. This map becomes a cornerstone for efficiently exploring and validating word squares. With the prefix map ready, we move on to building the word squares using a backtracking approach. The idea is to construct the square row by row, ensuring that the columns also form valid words. A square is considered complete when it has as many rows as the length of the input words, which in this case is 4. We start by choosing a word, such as wall, as the first row. Then, for the second row, we need a word that matches the prefix formed by the second column, which is a. Using the prefix map, we find area as a candidate, extending our square to wall area. For the third row, the prefix to match is lo, and the candidate lead fits. Similarly, the prefix for the fourth row is lad, and lady matches. This forms a complete square, which we save as a valid solution. The process doesn't stop here, as we continue trying other words as the first row. For instance, if we start the square with the word ball, we repeat the process of matching prefixes to build potential solutions. The second row must match the prefix a, and area fits. The third row needs to match lu, so we add lead. Finally, the fourth row must fit the prefix lad, and lady completes the square. This gives us another valid square, ball, area, lead, lady. By systematically exploring all possibilities, we identify all valid word squares. The final output includes the squares, wall, area, lead, lady, and ball, area, lead, lady. Key observations about this solution include how backtracking allows us to build word squares one row at a time while validating prefixes for the columns. The prefix map plays a crucial role in ensuring that prefix lookups are efficient, reducing unnecessary computations. Additionally, the algorithm exhaustively explores all possible starting words to ensure that no potential solutions are missed. This combination of backtracking and prefix mapping creates an optimized and systematic approach to solving the problem. To analyze the time complexity of the word squares problem, let's start by breaking it into two main components, building the prefix map and the backtracking process. First, consider the prefix map. For each word in the input list, we generate all possible prefixes, including the empty prefix. Since there are n words, and each word has k prefixes, the total number of prefixes processed is n times k. Appending a word to the list corresponding to a prefix is a constant time operation. Therefore, the total time complexity for constructing the prefix map is n*k. Now, moving on to the backtracking process. Here, the prefix map is used to find candidate words that can extend the word square. The recursion depth is k, which corresponds to the side length of the square. At each level of recursion, we calculate the prefix for the next row by concatenating characters from the first step rows. This operation requires O, step, time per step, and over k steps. This totals to O, k squared, time per square. Furthermore, at each step of recursion, we query the prefix map to retrieve all words matching the current prefix. Let B represent the maximum branching factor, which is the number of words matching any prefix. In the worst case, the algorithm explores b to the power of k combinations of words to construct a word square. Combining these factors, the backtracking process has a time complexity of O, n times b to the power of k times k squared, where the factor n comes from starting the process with each word in the list as the first row. Overall, the dominant term in the time complexity is O, n times b to the power of k times k squared. Next, let's evaluate the space complexity. First, consider the prefix map. For every prefix of every word, we store a list of words that match that prefix. Since each word has k prefixes, and there are n words, the total number of prefixes is at most n asterisk k. In the worst-case scenario, where all words match all prefixes, the total storage required for the prefix map is O, n squared. For the backtracking process, the recursion depth is k, and at each level, we store the current partial square. Since a square consists of k words, each of length k, this requires O, k squared, space. When combining these, the total space complexity is dominated by the prefix map, resulting in O, n squared. Finally, let's compare the optimized approach with the brute force method. In a brute force approach, we would generate all possible combinations of words and validate each one for the word square property. Checking a single combination involves verifying prefixes, which takes O, k squared, per square. Since there are n to the power of k possible combinations, the time complexity for brute force is O, n to the power of k asterisk k squared, which becomes infeasible for larger input sizes. In contrast, the optimized approach with the prefix map reduces the search space by leveraging prefix constraints. This gives a time complexity of O, n times b to the power of k times k squared, where the branching factor b is typically much smaller than n. Breaking it down further, in the best case, where all words have unique prefixes, b is minimized, and the time complexity simplifies to O, n asterisk k squared. In the average case, b is moderately smaller than n, and the time complexity depends on b, often written as O, n times b to the power of k times k squared. In the worst case, where all words share the same prefixes, b equals n, leading to a time complexity of O, n times n to the power of k times k squared. This illustrates how the prefix map significantly improves the feasibility of solving the problem for moderately sized inputs. One common mistake when solving the word squares problem is not pre-computing prefixes. If you're checking prefixes on the fly during the backtracking process, you might end up performing redundant computations repeatedly, which can significantly slow down your solution. Instead, it's better to pre-process the word list into a prefix hash map. This allows you to quickly look up valid prefixes without recalculating them, reducing the overall time complexity. Another frequent issue is ignoring word length constraints. To form valid word squares, all words must have the same length as the size of the square, denoted as n. If you include words of varying lengths, the algorithm will waste time attempting to form invalid squares. Lastly, many implementations suffer from inefficient backtracking. For example, using data structures like lists instead of sets to check prefixes can lead to linear searches, which increase runtime, especially with larger inputs. Optimizing your data structures is crucial for better performance. Skipping edge case testing is another common mistake. For instance, scenarios like an empty word list, a word square size of 1, or duplicate words in the input are often overlooked. These cases can lead to runtime errors or incorrect outputs if not handled properly. It's also important to avoid overcomplicating the problem. A common pitfall is attempting to generate all possible word combinations first and then validating them. This approach results in an exponential number of invalid combinations and quickly becomes unmanageable for larger inputs. Instead, focus on building word squares incrementally during the backtracking process. By ensuring each step leads to a valid square, you avoid exploring unnecessary paths, making your solution far more efficient. During interviews, optimizing your approach to handling prefixes is often a key area of focus. Interviewers want to see that you can move beyond brute force methods, so highlight the use of a prefix hash map or tree to eliminate redundant computations. Be prepared to discuss the trade-offs between these approaches, such as the higher memory usage of a tree versus the slightly slower access time of a hash map. Incremental thinking is also critical. Emphasize how building valid word squares step by step helps you avoid the inefficiencies of generating all combinations up front. Don't forget to explicitly mention edge cases, as this demonstrates thoroughness. Lastly, showcasing the reusability of prefix-based structures is a great way to stand out. For example, the same techniques can be applied to other problems, like autocomplete systems or word searches. Some related problems to explore include word search and search suggestion system, which share similar optimization strategies. There are several alternative approaches to solving the word squares problem, each with its own trade-offs. One option is tree-based backtracking, where you store all words in a tree. This allows for highly efficient prefix lookups during backtracking, but it comes at the cost of higher memory usage to construct the tree. Another approach is to use a hash map to pre-compute prefixes. Here, the keys are prefixes, and the values are lists of words matching those prefixes. While this method is easier to implement and uses less memory than a tree, hash map access might be slightly slower. Finally, there's the brute force approach, where you generate all possible word squares and validate each one. While simple to implement, this approach is computationally expensive and impractical for larger inputs. The key takeaway is that efficient prefix handling is central to solving this problem optimally. Always validate words incrementally to save computation, and remember that pre-processing, whether via a tree or a hash map, can significantly improve performance. Great job! We've successfully solved the word squares problem. Today, we learned how to use prefix-based searches and recursive backtracking to handle word constraints efficiently. Remember to practice using tries for similar problems. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!